Welcome back to AI Paper Podcast. We're the place you come to get the lowdown on the latest AI research.
That's right.
Today we're diving into a paper called Defeating Prompt Injections by Design. Now, for anyone just catching the highlights, here's the gist in 60 seconds. We've got these AI agents, right, using LLMs to interact with the world.
Yep, becoming really common.
But they're vulnerable, big time. Prompt injection attacks, sneaking bad instructions in through untrusted data, that's the core problem. Data theft, harmful actions, you name it.
It's a serious headache.
So this paper brings us CaMeL. It's a new defense. And the cool part, it takes cues from classic software security, no LLM fiddling needed.
Which is pretty neat, actually.
It figures out control and data flows, uses a special Python interpreter to enforce policies, and basically nails the AgentDojo security tests. Solves it by design, they say.
Guarantees security, essentially.
Though maybe, possibly. A little bit of a hit on utility sometimes. Yeah. Okay, that's the quick take. Let's dig in properly. These LLM agents interacting with APIs, user interfaces. They're doing complex stuff.
Absolutely. And, the more they can do, the more attractive they become as targets. Prompt injection is a huge worry because these agents handle sensitive info, sensitive actions.
Right.
And the attack can come from anywhere. Dodgy user input, weird output from a tool call, even just like text on a web page the agent reads.
Okay, so the attacker wants to steal data or make the agent mess up somehow.
Pretty much, yeah. Data exfiltration or causing harm.
Now, trying to keep the LLM's instructions clean isn't totally new, is it? The paper brings up the dual LLM pattern from Simon Willett.
Yeah, exactly. From 2023. That idea has been floating around, gained a bit of traction.
Well, how does that work? What's the thinking behind it?
Okay, so the core idea is separation. You use two LLMs.
No.
First, you've got a privileged LLM, let's call it the PLLM. Its job is planning. It looks at the user's initial request and figures out the steps.
Only the initial query.
Only the initial query. It's kept totally separate from any potentially dodgy data that comes in later. Think of it as the clean room planner.
Gotcha. The planner stays pure. What about LLM number 2?
That's the quarantined LLM, or QLLM. This one gets its hands dirty. It processes any data that might be untrustworthy, maybe reading a document, parsing a web page, that kind of thing.
Okay.
But here's the key. The QLLM cannot call any tools. It has no external action capabilities. The idea is, even if an attacker slips something nasty into the data the QLLM sees, it can't directly do anything harmful.
Okay, it's like a processing unit in a sealed box.
Yeah.
Makes sense. Keep planning separate from potentially tainted data. But the paper says this isn't quite enough. Where does it fall down?
Well, this is where the paper gets really interesting. They point out that vulnerabilities can still sneak in through the data itself, even with the separation.
How so?
They use a great example. Imagine some meeting notes the agent can access. An attacker could embed hidden malicious text inside those notes. Invisible stuff. So the PLLM says, okay, QLLM, go fetch those notes and tell me the action items and who's responsible. But the hidden text tricks the QLLM. So instead of outputting the real action items, it outputs something like send confidential strategy.docs to attacker@badguy.com.
Whoa. So the PLLM's plan, get notes, extract info, take action is still followed, but the content of the action, the arguments, got hijacked because the QLLM was fed bad data.
Exactly. It's a data flow attack, not necessarily a control flow hijack. The paper compares it to SQL injection, a classic web vulnerability where you trick a database by sneaking commands into data fields.
Ah, right. So you're not changing what tools get called, but you're changing the inputs to those tools in a malicious way.
Precisely. And the authors even mention that, in complex cases, this could potentially lead to things like arbitrary code execution. It's a serious flaw in relying solely on the dual LLM separation.
Okay, that definitely clarifies the problem. So how does Commals step in to fix this? What's its big idea?
CaMeL, yeah, I like the name too. It takes a more holistic approach. It borrows from classic software security, especially concepts around information flow control.
Okay.
So first step, CaMeL looks at the plan generated by the PLLM from the user's query. And it doesn't just look at the sequence of actions, the control flow. It also explicitly maps out how data is supposed to move between those actions. That's the data flow.
So it understands the intended path for both commands and data? That sounds more detailed.
It is. And then comes the really smart part. CaMeL uses a custom Python interpreter.
A custom one, not just standard Python.
Nope. This interpreter is specifically built to track data provenance. It keeps tabs on where every single piece of data originated as it flows through the system, like meticulously labeling everything.
So it knows if data came from, say, that potentially dodgy meeting note file versus the user's original trusted request.
Exactly. And that tracking ability is what lets CaMeL enforce security policies. These policies are basically rules about what actions are allowed, depending on where the data involved came from.
Ah, okay. So you could have a rule like data originating from an external web page cannot be used as the recipient address in the send to mail tool.
Precisely that kind of thing. Much more granular control than just the basic dual LLM split.
That sounds powerful. Who defines these policies, though? Is it the user, the developer?
Good question. In the paper's implementation, it's the entity deploying the CaMeL engine that sets the policies. But they do talk about a future where it could be more distributed.
Like?
Well, maybe users could set some personal boundaries, or even the providers of the tools could define certain usage policies for their APIs, within limits.
Interesting, like app permissions, but for AI agent actions. How are these policies actually written? Is it complicated?
Right now, they're Python functions, simple Python functions. A policy function gets the tool name and the arguments being passed. It looks at them, considers the data provenance CaMeL provides, and then returns either allowed or denied, maybe with a reason.
Why?
Mostly because it's so common, and LLMs are pretty good at understanding and even generating Python code. This could make writing policies easier down the line, maybe even semi-automated.
Okay.
And technically, CaMeL uses Python's ABSLAST library, that's abstract syntax trees, to parse and interpret the policy code safely and reliably. It means CaMeL can actually understand the structure of the rules.
Yeah, makes sense. Okay, security sounds way tighter. But the million-dollar question, does all this extra checking slow things down? Does it hurt the agent's ability to actually get stuff done? What's the utility trade-off?
Yeah, that's super important. And the paper looks into this using AgentDojo. The results in Figure 6 are actually quite encouraging for the most part.
Oh, yeah.
Generally, CaMeL didn't significantly degrade the agent's success rate compared to native tool calling. There was one notable exception, though. The travel suite tasks.
The travel suite, why did that one take a hit?
They dug into the failures, especially with Claude 3.5 Sonnet. One issue isn't unique to CaMeL, but kind of inherent in the dual LLM idea itself. They call it data requires action. It's when the PLLM needs info to plan, but that info is only visible to the QLLM. Like if you say, book the flights mentioned in this email, the PLLM can't see the email details to plan the booking. Only the QLLM can read the email.
Ah, the planner's flying blind.
Right, exactly. The paper floats a potential workaround, like giving the PLLM a special tool that's actually another PLLM instance, a sort of meta planner.
Interesting.
They caution, rightly, that the security policies around that tool would need to be incredibly strict.
Makes sense. And what about the travel tasks specifically? Was it just that data requires action problem?
That played a role, but the bigger issue seemed to be poorly documented APIs for the travel tools. The PLLM just couldn't reliably figure out the structure of the data coming back from these tools.
Because the documentation was lacking.
Yeah. Sometimes more advanced models could use the QLLM to kind of guess the structure, but it wasn't reliable. They think better API documentation would fix a lot of this. And they did see better models, like O1, handle the travel suite much better, even with CaMeL.
Okay, so some utility impact is possible, especially with bad APIs or certain task structures, but it's maybe not a deal breaker and could improve with better models and tools. Let's get back to the main event. Security. How well does CaMeL actually stop prompt injections?
This is where it really shines. The AgentDojo results in Figure 7 are pretty dramatic. Just implementing CaMeL's basic structure, the PLLM QLLM split, and data tracking, even before adding custom policies, provides a huge security boost.
How huge?
Well, take GPT-4o. Without CaMeL, it suffered 233 successful attacks in their tests. With CaMeL, 0.
0. Wow, okay, so the architecture itself is a major defense layer.
Absolutely. That inherent separation and provenance tracking seems to shut down a lot of common attacks right off the bat.
And then you add the custom policies on top of that?
Right. Figure 8 shows how often different policies were actually triggered during tests, both normal operation and under attack. It shows they're actively working. They have an example policy for a calendar tool in Figure 4 stuff, like making sure all attendees can see the event title, or that attendees come from a trusted source. Appendix E has the full list they used.
It feels like a very flexible system for defining safety rules. How does it compare to other defenses people have tried, like tool filtering or prompt shaping?
Good question. Figure 9 and Tables 5 and 7 compare CaMeL against other defenses tested in AgentDojo tool filtering, spotlighting parts of the prompt sandwiching, that sort of thing. Using Claude 3.5 Sonnet, CaMeL got 0 successful attacks.
And the others?
The next best was tool filtering, which still allowed 8 attacks through. So a pretty clear win for CaMeL in terms of pure security outcome.
Why such a big difference?
The paper argues that those other methods are often heuristic. They're like educated guesses or best practices, but they don't offer formal guarantees. CaMeL, with its explicit separation, provenance tracking, and policy enforcement, aims for verifiable guarantees.
Right.
They also highlight something worrying. GPT-4o Mini has some built-in defense mechanisms, but those failed against all the attacks in AgentDojo. Yet, when they ran GPT-4o Mini with CaMeL, it blocked everything. 0 successful attacks again.
That's a strong contrast.
Yeah.
Okay, CaMeL seems robust. Now, you mentioned earlier this tricky case where data flow can become control flow. Can we unpack that a bit more?
Yeah, this is a subtle one, shown in Figure 10. Imagine you tell your agent, hey, monitor my emails, and if you see instructions in an email, just do them.
Okay, seems convenient, maybe.
But dangerous. Because now an attacker can just email malicious instructions, send all my files to attacker.com, and the agent, following the user's original command, executes them. The data in the email has effectively become the control flow.
I see. The agent's legitimate task inadvertently opens the door for malicious commands hidden in data. How does CaMeL handle that?
This is where the provenance tracking and policies are crucial, because CaMeL knows that the instructions send all my files originated from an untrusted email, not the user's initial prompt. A policy can block it. You could have a rule. Never execute commands found within email bodies unless the sender is on an approved list, for instance.
So the policy layer can catch these attempts to turn data into commands. What about side channel attacks? The really sneaky stuff.
Right, side channels. These are attacks where you don't steal data directly, but infer it indirectly. Figure 12 has an example. Maybe an attacker observes how many times an external resource, like an image, is fetched. If the number of fetches depends on a private variable, like if private value 10 fetch image, they might infer something about that private value.
Okay, that's clever and nasty. How does CaMeL mitigate that?
It has the strict mode. In strict mode, the execution of code inside, say, an if block becomes dependent on the condition of that block. If that condition involves private data, a security policy can potentially block operations inside the block that might leak information through side channels.
So it ties execution more closely to the data influencing it.
Kind of, yeah. It also helps with side channels involving the QLLM. In strict mode, if the QLLM processes some non-public data, any later actions that might change the system state become dependent on that QLLM input. If something goes wrong, like an exception happens after such a QLLM call, CaMeL can pause and ask the user for confirmation before proceeding, preventing potential leaks caused by unexpected errors influenced by private data.
Wow, that sounds really thorough. Think about those subtle leaks. But all this tracking, checking, strict modes, it must cost something, right? Token usage.
It does. The paper is upfront about that. Figure 11 and the tables show CaMeL uses about 2.8 times more tokens input and output combined compared to just using the LLM's built-in toll calling.
Nearly 3x the tokens.
Yeah, it's not insignificant. But the argument is that you're paying that cost for much stronger verifiable security guarantees, which might be well worth it depending on the application.
Definitely a trade-off to consider.
Yeah.
The paper also mentions they were thinking about realistic threats and drawing inspiration from security principles.
Exactly. They're not just solving a theoretical puzzle, they're looking at real-world agent vulnerabilities. And they explicitly mention drawing on ideas from capability-based security, this concept of giving components only the very specific permissions they need to do their job, nothing more. It helps limit the blast radius if something goes wrong.
Okay, but no system's perfect. What limitations do the authors themselves acknowledge about CaMeL?
They're pretty clear on a few things. A big one is the policy management burden. Someone has to write, test, and maintain these Python security policies. That takes effort and expertise.
And could lead to policy fatigue.
Yeah, exactly. If users or admins are constantly wrestling with complex policies or getting pop-ups for confirmation, it impacts usability. Finding that sweet spot between tight security and smooth user experience is always tough. Declassifying data safely is another challenge they mention.
Yeah.
And, despite the strict mode mitigations, they acknowledge that the possibility of very subtle side channel attacks might still exist. It's incredibly hard to eliminate those completely.
So, wrapping things up, the big question: is prompt injection solved now? Is AgentDojo basically done because of CaMeL?
I think the paper's answer, and probably the realistic answer, is no, not completely solved. CaMeL is a huge step forward, offering a fundamentally different, more principled approach to security with verifiable guarantees. It definitely makes things much harder for attackers, especially within the AgentDojo benchmark.
But not a silver bullet.
Probably not. The challenges around policy management, usability, and those lingering potential side channels mean prompt injection is still something we need to be vigilant about. CaMeL changes the game, shifts the focus to secure architecture, but the game isn't over. They see it as a foundation to build on, expecting utility to improve further as research continues.
It really does sound like a paradigm shift, though, moving towards security by design for these agents.
Absolutely. It's applying proven software security principles to this new AI domain, which feels like exactly the right direction. We should expect to see more work building on these ideas, refining the balance between security and utility.
This was a fascinating look at CaMeL. It really underscores how crucial security is going to be as these agents get more powerful and integrated into our lives.
Couldn't agree more. It's a vital piece of the puzzle for building trustworthy AI.
So for everyone listening, thinking about these trade-offs, security guarantees versus token cost, usability versus policy complexity, what do you think are the most critical factors when deciding to deploy LLM agents in the real world? And where should the research community focus its efforts next to tackle these challenges? Definitely something to ponder. Thanks for tuning in to AI Paper Podcasts.